Hi, in this series I'll be going over AP Physics 1. This should be used as preparation for the AP test. And yeah, we're going to be starting off with kinematics. So here's a 2002 kinematics FRQ. I guess the plan is just to go through each unit or topic in AP Physics 1, do like one or two FRQs, and then move on to the next one. So yeah, we're starting off with kinematics. This question is: a model rocket is launched vertically with an engine that is ignited at time t equals 0, as shown above. The engine provides an upward acceleration of 30 meters per second squared for 2 seconds. Upon reaching its maximum height, the rocket deploys a parachute and then descends vertically to the ground. Determine the speed of the rocket after the 2 seconds of the engine, 2 seconds firing of the engine. Okay, so we know that our acceleration is going to be equal to 30 meters per second squared. We want to find the speed of the rocket after 2 seconds. Well, we can use the kinematic equation. V final is equal to V initial plus acceleration times time. So in this case, it starts at rest, so V naught or V initial is equal to 0. So it's just going to be 0 plus the acceleration we know is 30, and the time is 2. So we have 60 meters per second. That's part A. Part B says, what's the maximum height? What maximum height will the rocket reach? Okay, so we know that over time, the first 2 seconds are going to be acceleration. So we know that our final velocity after the 2 seconds of acceleration is going to be 60. And in the first 2 seconds, so wait, we'll just set that as V naught for now. But the maximum height the rocket will reach, let's say after these 2 seconds, is given by x of t is equal to 1/2 at squared. We know that a is equal to 30, so we have 1/2 30 t squared would just be 4 because 2 squared. So we're going to have 60 here. So in the first 2 seconds, it goes 60 meters up. And then we have a velocity of 60 meters per second, and gravity basically slows down the rocket until it reaches its maximum height. And we can use the kinematic equation V final squared is equal to V naught squared plus 2AD. Here, the only acceleration is going to be gravity, and we could treat this gravity as being 10 meters per second squared. So V final is just going to be 0, so 0 squared is equal to V naught squared, we've established that to be 60 squared, minus 2 times 10 times whatever distance. We're subtracting because the acceleration is going in the opposite direction of the rocket, so it's slowing down the rocket. And solving for D, we just get 60 squared over 20, which is, this is D, and this is going to be equal to 3 times 60, so 180. All right, so after 2 seconds, the initial 2 seconds, it goes 180 meters more higher. So we're going to add this initial 2 seconds plus this 180, we're going to get 240 meters. That's the maximum height. And then part C says, at what time after t equals 0 will the maximum height be reached? So basically, we know that the first 2 seconds are going to be the first 60 meters, and then the last some seconds is going to be the last 180. So we could just use a regular velocity equation for this. We know that V final is equal to V naught plus AT. And in this case, V final is just going to be 0. We're going to find the period of time from the after 2 seconds to the end. So it's going to be 0 is equal to 60 minus, because gravity, 10 times t. Solving for t, we get t is equal to 6. So this is going to be from the 60 meters up to the 240 meters up. So now we need to add the initial 2 seconds as well. So 2 plus 6, we're going to have a final of 8 seconds. Okay, so moving on to dynamics or forces, we're going to be doing the 1985 FRQ. So two 10-kilogram boxes are connected by a massless string that passes over a massless, frictionless pulley as shown above. The boxes remain at rest, with one on the right hanging vertically. So this one's hanging vertically, as you can see, and the one on the left 2 meters from the bottom. so this distance 2 meters from the bottom, of an inclined plane that makes an angle of 60. Okay, this is 60 with the horizontal. The coefficients of kinetic friction and static friction between the left-hand box and the plane are 0.15 and 0.3, respectively. You may use G as 10, sin 60. Okay. What is the tension of the string? All right, one really important thing to note is that the boxes remain at rest. And what do we know about that? That means the forces are going to be equal, meaning this force and this force have to be equal because the boxes are not moving at all. If one force overpowers the other force, or so basically if one force is greater than the other force, then that means the boxes would have, they would be moving. The system would have moving boxes. All right, so what force is being applied to the string by this 10 kilogram box? Actually, we'll just draw like forces. So we know that we have a force here. This is going to be force of gravity. Here is force of tension. And this same box applies a force of tension, or the string applies a force of tension this way. And here we just have regular gravity for, I'll just say this is G1 and this is G2. Okay. So we know that for this box specifically, we're going to have, actually, we don't even need that. We know that the force of tension is just going to be equal to the force of G2 because this system is at rest. So this is just going to give us, so for part A, we're going to have Fg2 is equal to Ft, force of tension, and then Fg2 is equal to mg. And in this case, it's going to be 10 times 10, where 10 is kilograms, 10 is gravity, and this is equal to 100 newtons. So that's what force of tension is. Okay, on the diagram, we just do it on here. Draw and label all the forces acting on the box that is on the plane. All right, so obviously we have normal force going this way. Then we have force of gravity going this way. And then we have the tension force going this way. Cool. Determine the magnitude of the frictional force acting on the box on the plane. Okay. All right, so basically, what's the friction force on this box right here? All right, so first, how do we even calculate friction force? We know that friction force is going to be normal force times whatever coefficient of friction that you have. And then we also know that since this box is at rest, we have this force right here, which is going to be our gravity, and this force right here, which is going to be tension. Oh wait, that reminds me. That means I missed a force, and that's going to be friction right here. Okay, so we have friction, tension, force of gravity, and normal force. We have 4 forces on this box. Okay, so that means these 2 upward forces right here, I'll put this in blue. These 2 upward forces have to equal this force of gravity, since they're going to cancel out, and then the box will be at rest. So how do we find this force of gravity right here first? This is just going to be F of G1, and this is just going to be mg sine theta. In this case, theta is equal to 60, and it says you can use 0.87. I'll just use root 3 over 2. But yeah, we're going to have 10 times, which is the mass, times gravity, 10 times sine 60, or 100 times root 3 over 2, or just 50 root 3. Can't box it. It's not the answer. All right, so that's force of gravity. And this is going to be equal to the force of friction plus the force of tension. And this is equal to force of gravity 1. We want to find force of friction, so just going to be Fg1 minus Ft is equal to F lowercase f. So 50 root 3 minus 100 is equal to F lowercase f. And the magnitude of this is just going to give us around 13 newtons. All right, so in dynamics, there are going to be two parts. There's going to be linear dynamics and circular dynamics, or circular motion. So here is the 2001 circular dynamics FRQ. So a ball of mass m is attached to a string of length r and negligible mass. The ball moves clockwise in a vertical circle as shown above. When the ball is at point P, the string is horizontal, and when the ball is at point Q, it's at the bottom of the circle. Point Z is at the top of the circle. Air resistance is negligible. Express all algebraic answers in terms of the given quantities and fundamental constants. Okay. On the figures below, draw and label all forces exerted on the ball when it is at points P and Q respectively. Okay, so at point P, obviously we have the force of gravity here. But since it is undergoing circular motion, there's also going to be a centripetal force. And this is given by the force of tension here. This is what supplies the centripetal force. And then at point Q, we're going to have force of gravity going down. And of course, force of tension going up. Let me erase that and write it so it does not look like I've vomited on my screen. Okay. Derive an expression, part B. For V min, the minimum speed the ball can have at point Z, so the top of the circle, without leaving the circular path. Okay, so basically this is when the force of tension is equal to the force of gravity. Sorry, the force of gravity is the only thing supplying the centripetal force, and the force of tension is 0. So we're going to have mg is equal to mv squared over r. And since the force of tension is 0, this is why it's the minimum velocity. But yeah, and then we can solve for v. So m's cancel out. We're going to have gr is equal to v squared, and then v is equal to square root of gr. Looking at part C, the maximum tension the string can have without breaking is Tmax. Derive an expression for Vmax, the maximum the speed can have at ball or at point Q without breaking the string. Okay, so we're going to have Tmax here minus mg. So basically the maximum tension minus mg, this is going to give us the maximum centripetal force, is equal to mv squared over r. And then we could just solve for v in terms of Tmax. So we're going to have r times Tmax minus mg all over m, and then square root it, and then we get Vmax. Here, I'll put Vmax. This looks ugly, but I think that's the right answer. Cool. And then part D, I don't think we need to write this down. Suppose the string breaks at the instant the ball is at point P, so on this side right here. Describe the motion of the ball immediately after the string breaks. Okay, so here the only direction that it's going is up, right? And the moment the string breaks, force of tension doesn't matter. There's no tension in the string anymore. So the only force, or I guess direction that the ball was going, was up at this moment. I'll just put this in green. This is not being part of as part A. I'll just illustrate it here. So it's just going up right now at point P. There's no more force of tension, meaning the only thing that's going to be on the point on the ball at point P after it breaks is the force of gravity, and there's going to be the upward direction that it's in, meaning the direction of the ball is just going to be up. It's just going to keep moving up, and then it's going to stop, and then it's going to come back down, and yeah.